All right, so I kind of manufactured a slide here from stuff that we've looked at previously. I didn't originally have this slide here, but I think it's really useful to go through before we move on to the next slide. And so what we should notice is that, of course, this is the circuit that we had been looking at previously. My voltage and my current across the resistor are in phase. And so we get this always positive average power dissipated by the resistor, okay? And we have this average value that we found. But what's really important to note is that these waveforms are also valid if we are looking at the power, not the power dissipated by the resistor, but the power supplied by the source, okay? So if we, right here, we're looking at V of t, which is the voltage across the resistor. But we could have also been looking at Vs of t, which is the power supplied by the source, right? If I write Vs of t, it's equal to V of t here, which is 10 times the sine of omega t volts, right? Which is exactly what we have for V of t. And if I look at the current leaving the source, right, it's in the same direction as the current flowing through the resistor, the way I defined it. So I could say that that current, I could call that Is of t. That's equal to I of t. So Is of t is equal to I of t, which is equal to 10 times the sine of omega t milliamps, right? So these waveforms are the identical waveforms I would see, especially, I mean, it makes sense, right? The voltage source and the resistor are in parallel. They're also in series. Their currents and their voltages will be identical. So this should make sense, but I need to make this point that my average power supplied, right, is equal to my P average dissipated in the resistor, right? And so if I were looking at this power waveform down here, this would be the power supplied by my source, which is the power dissipated by my resistor, okay? So they have the exact same waveform. As if my supply is supplying energy, my resistor is dissipating it at the exact same rate, is basically what this is saying. So if positive power here means that my source is supplying energy, what would happen if this power went negative, right? If we ended up with a region down here of negative power, well, that would mean that energy is actually flowing back into the source. It's not actually being dissipated, rather it's flowing back into the source, okay? And what you might notice is that if this signal comes down into the negative, then the average value would move down as well, and we would end up with less of an average power dissipation for our resistor. What could possibly cause the average power to go negative, though? We noted that if our voltage and our current are in phase, and they both have the same zeros and they both have the same peaks, then the average power always stays positive. So what it would take for our average power to go negative, it would take our voltage being positive and our current being negative for some span of time, or vice versa. It could be the other quantities. As long as our voltage and our current have the same sign at all times, our power is always going to look like this. That only happens when there is no phase shift between the two signals. So what happens when the load is not purely resistive is at the source, right? So if I were to draw a circuit here, this is my source, and I have some load here that's not necessarily purely resistive. Now, when I examine this Vs of t, right, and I examine Is of t, I guess I should draw this Vs of t in blue because that's what I'm plotting in this slide. When I plot these Vs of t and Is of t, I see that they're no longer in phase. And so if I were to track this, I can see that for some, from here to here, they have the same sign, which is great. But from here to here, they have the same sign. But there's a period where my current is positive and my voltage is negative, right? During this time span right here. And so what happens to my power during that time is that my power actually dips into the negative region. And that means that power is not being supplied during that little time. Rather, it's being sent back into the source. Energy is not being dissipated by my load. It's being sent back into the source, and that occurs due to that phase shift between the voltage and the current, okay? And so there is obviously some issue here because we have the exact same signal height, like the amplitude, but the average value moves down because the signal is starting to shift to where, you know, its average value is dropping. And so we can't just take VS RMS times IS RMS when we don't have a purely resistive load, because we have to account for this phase shift between the voltage and the current. Okay, so if I were to draw that, it would be this phase shift here in degrees. If this is omega t in degrees, I guess I have it, you know, it could be an angle in degrees or in radians, but really we normally write it in degrees. We need to account for that, the difference between the phase of the voltage and the current. That'll be my phi. And how do we account for it? Well, it just so happens that we can pretty easily still determine the average power, which we calculated previously by just doing IS RMS times VS RMS. Now we just need to add this scaling term here, the cosine of the phase, right? The phase, again, being the difference in phase between the voltage and the current. As long as we calculate that phase shift, cosine will go between 0 and 1, right? The cosine of that angle will go between 0 and 1. And so it'll basically take my ISR, or my IRMS and my VRMS, which I calculated previously as my average power, and it'll just scale it to a value between 0 and 1. So it is possible for the phase shift to be such that this entire cosine term goes to 0, and I get 0 average power dissipated by my load. That is the case when we have a purely capacitive or a purely inductive load. If we have some combination of resistance and capacitance or inductance, that won't be the case. But if we have a purely resistive or a purely capacitive load, we can end up with 0 average power dissipated, because this cosine term can go to 0 under the correct conditions for this phase shift. Okay, so some quick notes on this function here. Let me just erase my little line through the cosine. Quick notes on this function here. For a purely resistive load, we already saw the product of the RMS and the voltage and current. Well, what's the case? Well, that's when the phi is 0 here, right? Phi is 0. So this cosine of 0 goes to 1, and I'm just left with I RMS times V RMS, which is what we saw previously. For a reactive load, which is a load that doesn't just contain resistances, it has some inductance, some capacitance, one or the other, or even both. We need the product of the RMS voltage and the RMS current again, but scaled down due to the phase shift, right? That's this downward scaling of the average value due to that phase shift. And it just so happens that you can just multiply it by the cosine of the phase shift. It's all trigonometry, and that is the formula that we're going to need to use for the average power dissipated, or actually the average power supplied by the source in the presence of a phase shift, okay? I'm talking about apparent power here. We haven't talked about that yet. We're going to talk about it pretty soon. I think that's one of the upcoming slides. But basically, the average power is written in terms of two things. It's written in terms of something called the apparent power, which is just IRMS times VRMS, we've seen before, and the power factor, which is just the cosine of the phase shift between the voltage and the current. So those are just basically the names for these two terms. They're important. You'll see these pop up quite often. Something might ask you to just find the apparent power of a circuit. Something might ask you to just find the power factor of the circuit. And so as long as you know how to set up this expression, you can always find those pretty easily. Okay? And so I'm going to go ahead and end this video. Let me see what's next. Oh, in the next video, I'm going to talk about an alternative way that you can find the average power. It's basically just an alternative version of this function. Again, another special case where if we only have sinusoids, which is often the case, we can write another version of this expression, which is even easier and allows us to bypass completely the RMS values. Okay, so I'm going to end this video here, and we'll talk about that one in the next video.